Okay. Hello, everyone. Welcome to another session with me. Today, I will again be discussing some questions from Basic Real Analysis course, NPTEL course offered by Professor I. K. Rana from IT Bombay. So, this is 6 week discussion and helping session. So, in between, if you find any difficulty understanding any argument, uh, you can unmute yourself, ask question. You can type in the chat box, whatever suits you. Don't feel hesitate to ask questions. So I have prepared. So as usual, I have prepared in these question in two parts. So in first part, we will do some calculative problems, problems which involve some calculations. In the second half, we will do some questions based on the concept theory that we have read about directional derivative, derivatives, continuity, and so on. Okay. So without any further delay, let us begin with today's session. So Um, so let me start with introducing myself. I am Prerak from Iser Bhopal. I conduct these weekly discussion with you guys, and this is another 2 hour live session. Uh, and the recording of this session will be uploaded on my YouTube channel named Maths with Prerak. You can find the recording, a recording of this session by uh, the next morning tomorrow. Okay. Okay. So this is the first question that we have to discuss today. So in this question, we need to use the definition to find out the derivative of each of the following function. So before going into directly solving this problem, let me just first recall what is a differentiation. How do we define a differentiation? So we define differentiation for a real valued function on a real variable. So we start with a real valued function on a real variable. We say we say f is differentiable. We say f is differentiable at x naught in R if uh, the following limit h tends to 0, f of x naught plus h minus f of x naught divided by h exist. Okay, so again, we need to compute some limit in order to say that the function is differentiable at a point or not. Okay, so what limit we are going to calculate? We are going to calculate this limit in particular, which is limit h tends to 0, f of x naught plus h minus f of x naught divided by h. Okay, so yes, so after this, whatever is this limit, so we call that to be, we denoted this limit by f prime of at x naught. Okay, so we denote the limit to be f prime of at x naught. So I am assuming that you guys are familiar with the limit of a function. I'm not going to recall the limit of the function again. So if you have any doubt, you can ask me now. Um, yeah. So this is how we will this denote the differentiation of the function. Any question? Okay. So now the idea to solve this question is to use this definition to find out the differentiation of each of this function. Okay. So I think if you guys have studied mathematics in your 12th standard, you already know the differentiation of these functions. But we want to find out the differentiation using the first principle, in particular using this definition. Okay, so let us calculate this one by one. So so let me start with a, which is this function fx equal to fx fx is equal to x cube for all x in R3. This is, for those who don't know, this is a symbol for all. Okay. Now we want to use the we want to find out the differentiation. Okay, so let's say we find the differentiation at x naught in R, and this x naught is arbitrary chosen. Okay, so how do we find out this differentiation? Again, we need to find out this limit of this function, which is x naught plus h minus f of x naught divided by h. Now, what is f of x naught plus h? F of x naught plus h is x naught plus h whole cube minus, what is f of x naught? It is x naught cube divided by h. Okay. Now, we all know the formula for a plus b whole cube. Using that formula, what we will get? We will get this thing, x naught cube h cube 3x naught h x naught plus h minus x naught cube divided by 3. Okay, x naught cube get cancels out. Now in the remaining term of h cube plus 3x naught h, you can take h common and you can divide this h again. Okay, so what will you get as a result? We get that it is limit h tending to 0 h square plus 3x naught plus h. Okay, now uh, we know limit of individual functions. Individual means this is the first part, this is the second part. Limit of individual functions exists. So the limit of since the limit of individual function exists, so we can uh, say that the limit of each of the function. So limit of this function will be nothing but the sum of the limit of each of the function. So limit of the first function is 0. Limit of second function is going to be 3x naught times x naught, which is 3x naught square. Okay, so in particular, as a result, what we have gotten is f prime of x naught, f prime at x naught is equal to 3x naught square. Okay, and since the x naught was arbitrarily chosen, I can just simply write that f prime of x is nothing but 3x square. Okay, without loss of generality, I can further write this thing. So this completes the uh, first part of the first part of the question. Okay, is this clear? Okay, so now let's move on to discuss this b part. So in b part, we have gx equal to 1 over x, and this is defined for all non-zero real numbers. Again, using the first principle, we want to find out g prime of x naught, which is defined to be limit of this function, which is x naught plus h minus g of x naught divided by h. And now again, this what is g of x naught plus h? It is 1 over x naught plus h minus 1 over x naught divided by h. This whole limit is going to 0. This is going to be x naught minus h, uh, x naught times x naught plus h, and h also comes here. You can cancel out x naught by minus x naught. Whatever is remaining, just write down that part. It is going to be minus h, and now again minus h also gets cancelled by this h in the denominator, so you will be remaining with minus 1 on the top divided by x naught times x naught plus h. Now the function in the denominator makes sense. Okay, it exists. The limit of this function makes sense. Okay, as at h tends to 0, So this limit is going to be 1 over x naught times x naught, which is minus 1 over x naught square. So in particular, since x naught was chosen arbitrarily, I can say that g prime of x is minus 1 over x square. Okay. Yes. So now let us discuss another question, root of x. So in C part, uh, we have kx, we have hx given to be root of x for all x in R. Okay. So again, we want to find out the differentiation of h at x naught, again using the definition, limit h tending to 0, h of x naught plus h minus h of x naught divided by h. So let me take this function to be a different function. Let me take a different notation. Let us take px. Okay, so I don't want you to get confused with the notational part. This h with the real number h. So I don't want you to get confused with this. That's why I'm taking different notation. Okay, just a moment. Yeah, and now this first part is x naught plus h minus x naught divided by h. Now, in order to make life easier, we can multiply with this factor square root of h plus square root of x naught divided by h. The denominator also we multiply the same factor, but it's not going to be problematic in the denominator because we have the plus sign. So as I multiply, I get x naught plus h minus x naught, because a minus b times a plus b is equal to a square plus a square minus b square. That's what I'm doing. X naught plus h, as a square I will get, minus b will be minus b square will be x naught minus x naught divided by h. The denominator we have this. Okay, so again I can cancel this x naught by minus x naught. Now this h will cancels out in the second step. So what I am remaining with is this limit. I am remaining with this 1 over x naught plus h plus x naught, which is equal to, as h tends to 0, this will be equal to 1 over 2 square root x naught. Okay, so in other words, what can I say? I can say that differentiation of p at x is equal to 1 over 2 um, 1 over 2 square root of x. Okay, so now let's see D part of this question. In D part, we have 1 over square root of kx. So kx is a function which is defined to be this for all x in R. Sorry, for all x in R. Again, we try to find out its differentiation at x naught, which is nothing but limit h tending to 0 of kx plus h minus kx divided by h equal to 1 over square root of x plus h. Sorry, we have x naught over here. I missed that x naught. Yes. This whole thing divided by h. Now this whole thing is again, uh, I am getting a factor in terms of a square root in the numerator. So I want to get rid of that kind of part. So what I do again, I multiply the numerator and denominator by a factor with a positive sign. Okay, so that the numerator becomes a square minus b square type. So what I'm gonna do is I'm gonna multiply this whole thing okay, and as a result what will I get is this part. Okay, after cancelling out this x naught with x naught, I can cancel out this h with this h in the denominator, and as a result I will be left with this part. Okay, so as I if I put the limit, if I calculate the limit of this function in the denominator, I will get uh, so this function is defined for all non-zero values. Okay, at zero it's not defined. So as a result, I will get as minus 1 over yeah, minus 1 over yeah minus 1 over um, square root of x naught square times 2 times of x naught. Okay, so this will be the answer to this question. So I hope this all of these questions make sense to you, um, and you don't have any doubt in this in any of these questions. So I use the first principle. Basically, first I calculated this limit, and then whatever the limit, if this limit exists, it is said to be differentiable at x naught, and we define the derivative at x naught to be this limit. Okay, so we call this thing this is derivative of f at x naught. Okay, and this is nothing but the limit that you evaluate. Okay, so this question is done. Now we move on to discuss the next part. Any question till this point you may ask. Okay, no question, then we can go ahead and discuss this point two question. So in this point two question, you need to we have given a function hx, and this function has an inverse h inverse on R. We need to find out the value of h inverse prime at y at the point corresponding to x equal to 0, 1 and minus 1. Okay, so what does it make sense? First, let us see how does it make sense. So what is h inverse? So h inverse is a function from R to R. H inverse is a function from R to R such that if you precompose it with if you compose it with h, uh, you must get identity function on x. What do we mean by that? We mean that hx, you compose it with h inverse of this, then the answer will be x only. Okay, so in other words, which is equivalent to say that h inverse composition with h is equal to identity function on R. Okay, and vice versa. Yes, it doesn't matter where you compose it. If you precompose this h inverse with h, you will again get identity map. That's the definition of h inverse. Okay, so now what we have here, it is given that you have a function hx and it has an inverse h inverse. We don't know what that inverse is. Okay, now you need to find out the value. So you are asked to uh, find out the value of h inverse. Okay, derivative of h inverse at a point y. And what is this point y? This point y must be an image of h. Okay, and they are referring it these points to be the points corresponding to x equal to 0, x equal to 1 and x equal to minus 1. Okay, so these y are nothing but h equal to hx, where x takes these values. Okay, so in other words you need to you need to in other words you need to find out this derivative. You need to find out these three values, where each of yi, where yi is equal to h of xi. uh, so y naught is equal to h of 0, let's say. Y1 is equal to h of 1, y2 is equal to h of minus 1. Okay, so now what is y naught? So if I replace this value in this equation, so h of 0 is 1, so it is 1. H of 1 is 1 plus 2 plus 1, it is going to be 4, so it is 4. H of minus 1 is minus 1 minus 2 plus 1, so it will be minus 2. Okay, so you need to find out these values is at these four, as at these 3 points. Okay, now how do we do that? So the idea to do this is to use the composition of two functions. Okay, uh, so what is the composition of two functions? So we defined differentiation of composition of two functions. So let's say uh, I have a function f from R to R and a function g again from R to R. Okay, so this composition of function g composed with f makes sense. So it will again be a function from R to R. And how does it define this composition? How do we define the composition? So we define this composition of functions to be this way. First, we apply f on Rx, and whatever the value, whatever real number we get, we apply g on that. Okay, better way to write it as uh, R from R, some extended arrow to R to R. This is, if this is my g o f, then I first apply f and then I apply g on it. So I start with x, I go to fx, okay, and then I go to g of fx, or I apply x and I get to g of f of x. So these two values, this is how we define it to be. Okay, so this is what? This is a composition of two functions. Okay. Now once you get familiar with the idea of composition of two function, now it is now what happens when you differentiate this composite function? Okay, so this function is called composite function. The result of a composition is called composite function. So what happens to the differentiation of this composite function? Now you ask this question. So what happens if I differentiate this composite function at some point? So what happens to this if I try to differentiate it at a point? So this is called something. This is called chain rule. I'm not gonna give you the proof of this chain rule, but I'm going to use this chain rule. Okay. So what does it say? It says that this differentiation is going to be equal to g. Differentiation of g. First, you differentiate g at this point, x f of x naught. Okay. Times you then differentiate f at x naught. Okay. So there will be two differentiation involved. First, you differentiate g at fx naught, and then you differentiate f at x naught. Okay. So this is how you define the differentiation of a composite function. Okay. So yeah. So this is how you define the differentiation of two composite functions. So proof of this fact can be found in any standard textbook. One of such is Bartley-Shebert with. Okay, these are Bartley and Shebert are the author's name, so you can find proof of such rules in this book as well. Um and any you can follow any other standard textbook in basic real analysis. You will be able to find the proof of this fact. So I'm not going to prove this fact, but let us use this fact to solve our exercise. Okay. So now what do we need to find out? We need to find out these three. We need to find out these three values is okay. But so you may say that, sir, I know what is yi is. Now, if I can calculate what is h inverse, I can directly find out its derivative, and then I can evaluate that derivative at y inverse. So I will say like it is fine. You can do that. But in this question, it seems tricky to find out the derivative at. It is tricky to find out the inverse of this function. So we use a simpler, trickier approach. We use the chain rule. So we already know that h inverse composed with h of x naught is equal to the identity function x naught. Okay. So now, if I differentiate this thing, this will be equal to differentiating the identity function at x naught. Okay, because both are same function. So if you differentiate this right hand side function, it is equivalent to differentiating the left hand side function. Now, uh, what is this left hand side? Left hand side is nothing but the differentiation of a composite function, and we use the chain rule to solve this left hand side. Solving this left hand side, okay. Solving this left hand side, what do we get? We get h inverse differentiation of h inverse at h x naught, correct, times h differentiation of h at x naught. Okay, and the right hand side is what? So we know that a differentiation of identity is 1. Okay, you always get 1 as a result. So it is 1. Right hand side is 1. Now, this is your y naught. Okay, this is your y naught. So in particular, the formula for this will be this. If you may say the formulation, so the formula to find out the differentiation of h inverse at y naught is equal to 1 over h prime of x naught. Okay. So now we use this formula. So we have derived this formula. Now we use this formula to our question. So then what will be h inverse, derivative of h inverse of y naught? It will be 1 over h derivative of h at x naught. Okay, so if my x naught is 0, then h inverse, so first let us calculate what is h inverse of x. So h inverse of x is x cube plus 2x plus 1. So it is the differentiation of x cube plus 2x plus 1. Okay, now we use the differentiation. So if you differentiate the first term, it is going to be 3x, 3 times x square plus 2. Okay, and now the 3x square plus 2, if you evaluate this at 0, you will get 2. Okay, if you evaluate at x naught equal to 1, you get 5, and if you evaluate x naught equal to minus 1, you get 1. Okay, so uh, so what will be the h inverse? So what will be h inverse, derivative of h inverse? So it will be 1 over 2. In this case it will be 1 over 5. In this case it will be minus 1. Oh sorry, in this case it will be 1. Okay, so this will be your answer. So this is your y naught, this is your y1. Sorry, no, sorry, this is what, yeah. So these will be the answer. So this completes the proof of this question. So what we did in this question, so let me give you just think of this question for some time, and then we will go ahead. Okay, so let me quickly recall this question. That we had a function hx whose inverse exists, already given in the question. Now you are asked to find out the derivative of that function, uh, derivative of the inverse of that function at some point corresponding to some values of x. And how did we do that? Because the inverse, calculating inverse of this function was difficult. Okay, we try to use the chain rule. And how do we use the chain rule? By using this fact that h inverse composed with h is equal to identity. Okay, so we use the chain rule, which is nothing but the differentiation of a composite function, and then we derive to this formula that h inverse, differentiation of h inverse at y naught is nothing but equal to 1 over h naught, h inverse of at x naught. Okay, and then using this formula, we calculated the values at corresponding yi's. Okay. Yeah. So now let us move on to discuss this question number point 3. Sorry. So in this question, you need to prove that if you start with the even function and you calculate its derivative at any point, then its derivative turns out to be an odd function. Similarly, if you start with a differentiable odd function, its derivative turns out to be an even function. So let us see why is that the case. So the definition also given in this question that even function, a function is said to be even if f of minus x is equal to f of x for all values, for all real in R. Similarly, a function is said to be odd if f of minus x is equal to minus of fx. Okay. So assuming these definitions are clear to you, we can move ahead with the question. So it is, we need to prove that it is an even function. So let us start with an even function. Okay. So what is an even function? Even function is fx, f of minus x is equal to f of x. Okay. Now if you differentiate this function, so if you differentiate this function, so this function, if you differentiate basically this f of minus x uh, part. So this function can be think of as a composition of two functions, okay, where this function g is a real valued function on a real variable taking x to minus of x. Okay, so the second function is, you can think of g, which is just taking x to minus x. So now this function can we think of it as a composition of two functions. Now if you differentiate this composition, okay, at any point x naught, we again apply the chain rule. Okay, so it will be this kind of function. And now what is g prime of x naught? So g prime of x, we know it to be minus 1, correct? uh, and what is f prime of g x naught? So f prime at g x naught, which is this, we don't know what that value is, but we know this is going to be this. This is going to be the differentiation, because we know the derivative exists, it is given in the question. So and the derivative of g prime at x naught is minus 1. So as a result, we get it to be this. Now what was our what was our right hand side? Right hand side turns out to be minus of f prime of minus x, correct? Yes. Yeah. And what was our uh, yes, and what was our right hand side? Right hand side was f prime of minus x. Okay, so in other words, what we have proven is that f prime of minus x is equal to minus of f prime of minus x, uh, which means, which implies that f prime is an odd function. Okay, so if we start with an even function, its derivative is turns out to be an odd function. Similarly, if you start with an odd function, so let's say if I start with an odd function with this type of uh, behavior, sorry, f of minus x is equal to this. Again, uh, I can think of it as this, like this equation. Okay, this is also equivalent to the odd function definition. Now I again take again define g function. Okay, so this will look like this, where g is of g of x is minus of x. Now we perform the differentiation. So we take the differentiation of this whole thing. So we get f of g x naught, f prime of x at g x naught times g of x naught, okay, plus f of x naught equal to f prime of x naught equal to 0. Now again this value is minus 1. This is f prime of this thing, which is minus x, plus this is what? This is f prime at x naught I'm taking, so x naught, let's keep it x naught only. It is this only. So f prime of minus x is equal to minus of f prime of x naught, this thing, and now you can cancel out minus from minus, so you will get f prime of minus x naught is equal to f prime of x naught. Okay, which is which means that f prime is an odd is an even function, implying that f prime is even function. Okay, so if you start with an odd function, you get even function as its derivative. If you start with an even function, you get an odd function as its derivative. Okay, this is a simple question. I hope you guys have understood this part. So let's move on to discuss uh, the question point 4. Okay, now in this question, it is given that f is a differentiable function at c and f of c is equal to 0. Uh, you need to show that gx, which is equal to modulus of fx, is differentiable at c if and only if f prime of c is equal to 0. Okay, so it is again composition of two functions, modulus function uh, and fx. Okay, so we need to show that if gx is equal to modulus of fx, differentiable at c if and only if f prime of c is equal to 0. And we already have that f is differentiable at c and f of c is 0. So okay, so let's see this question. So now in order to find out the limit, uh, yeah, so we want to say that this is differentiable. Okay, what do we mean by that? It should be that, and now that means this limit of x tending to c, sorry, um, s tending to 0 of g of x plus h, c plus h minus g of c divided by h exists. Okay, so this is the first, this is the definition, the first principle. And now what is this g c plus h? The c plus h is nothing but f c plus h modulus of that minus f c. Okay, so now we already know that f of c is 0, so this reduces us to this case, that f of c plus h divided by modulus of this divided by 0 divided by h. Okay, now the now it is given that if it is differentiable. Okay, so now in this question you need to say that this function is differentiable at c if and only if f prime of c is equal to 0. So it is an if and only if statement, which is like by equivalent. So we will say that, so we will assume that it is differentiable at c. Okay, and then we will prove that f prime of c is equal to 0. So if it is differentiable at c, that means this limit exists. That means this limit also exists. Okay, so I'm assuming that it is, this is assuming this is differentiable. So uh, this limit exists. This limit exists. And what do we mean by when we say that this limit exists? So you can take now this limit uh, is equal to left hand limit when you approach 0 from the left hand side, which is 0 minus. And in that, if you approach 0 from left hand side, yes, if you approach 0 from the left hand side, um,
हेलो सर, नमस्कार.
yes.
Hello sir,
So
प्रणाम.
yeah.
Sir, can I see the question there?
So in simple words, if I want to say, this thing can be, if you approach from left hand side, it can be either positive or negative to whatever its value. Similarly, if you approach from right hand side also, it can be either positive or negative, because if you remove the modulus sign, this positive and negative will comes in
Hello sir.
with the function value. Okay. Now in either of the cases, these limits are going to be equal. Okay. And we already know these limits are now in either of the cases, it will be equal to f of c plus h. Let's say if it is minus, so you can think of f of c as c divided by h, and if it is positive, if the limit is positive, then you can think of f of c as you can think of subtracting f of c from it. Okay, so in either of the cases it makes sense. Okay, because f of c is 0. So what happens that this, and we know that this limit exists from the assumption that g prime c is differentiable. So we know that this limit exists, which implies that f prime at c exists. Okay, because this is equivalent to f prime of c. Okay, so the question is this. So you start with a differentiable function, which is differentiable at f and f of c is equal to 0. Then you need to show that g of x, which is defined to be modulus of fx, is differentiable at c if and only if f prime of c is equal to 0. Okay, so we have already given that it is differentiable at c. Okay, so we don't need to show that. So we start with the assumption that this limit exists, and now we need to show that f prime of c is equal to 0. Okay, so you don't need to go into this much. Yes, so let us try using the chain rule. So, so we have given that this is differentiable at c, which is nothing but modulus function composition with f at c is differentiable, which is nothing but f m prime of f of c uh, multiplied with f prime of c. Okay, now this modulus function of, and now this f of c is 0. Now modulus function at 0, it is not differentiable. We know that because the left hand limit and the right hand limit are not equal to 0. So this is only possible. So this limit, okay, so let me skip this question for now. I will come back to this question. I'm lost in argument at this moment. So I will discuss
Yeah,
a new
it's okay,
question
sir.
with you instead of discussing this question. So yeah, yeah, let's come back to this question. Question point 5. So in this question, uh, okay. So in question point 5, uh, you have fx, which is given to be x square times sine 1 over x, for x being non-zero and 0 when x is equal to 0. So now you need to say that this function f. So question is f differentiable at first of all when x is not equal to 0, and second at x equal to 0. Okay, so we will break it into two cases. So we need to show that f is differentiable or not in two cases. So if we start with x equal to non-zero, so if I start with x equal to non-zero, then my function fx is x square times sine 1 over x. Okay, so now uh, yes, so fx equal to x square times sine 1 over x. This function is differentiable, and you can even calculate this limit by using the product rule. So because this function is nothing but product of two differentiable functions, so it is differentiable. Sine 1 over x, sine of 1 over x is nothing but, can we think of as a composition of two functions. So first function is sine, okay, composed with another function, let's say g of x. So where g is a function from r to r, going from x going to 1 over x. Okay, so this sine 1 over x can we think of as a composition of two functions. And now this composition for x,
Hello, sir.
yeah, so for sine of g over x, yeah, sine of g over x,
Hello, sir.
this is a composition of functions.
Sir, am I audible, sir? Okay, sir. Am I audible, sir?
Okay, okay, so this can we think of it as a composition of two functions. Now each of the function is differentiable at x not equal to 0. This function is differentiable at x not equal to 0. Similarly, uh, sine is also differentiable at not equal to 0, and this, so this function differentiation makes sense. And how, if you differentiate this function, what will you get? You will first need to differentiate sine at gx naught. Okay, let's see, if you're differentiating at x naught, come and times g prime of x naught. Okay, sine differentiation at x naught. Now differentiation of sine is nothing but cos and 1 over x naught times 1 over x. Differentiation of 1 over x we have seen previously in the first question today, that it is nothing but minus 1 over uh, x square. Okay, so this will be the case, and now this function is
Sir, here what is the
is
g
a
of x
product of
function?
two differential function.
Sir,
I
what is
can't
g
hear
of x
you if
function?
you're trying to speak. I can't hear you.
Hello, sir. G of x function, sir.
So this g of x is the function that I'm defining.
Okay, okay.
So g of x, this sine 1 over x, can we think of as composition of two functions? First function is sine and the second function is g. What is g? G is nothing but r from r. G is a function from r to r where x going to 1 over x. Okay, so this sine 1 over x can be thought of as a composition of two functions, sine and g. It's composition of g with sine. Okay,
Okay, sir.
I can't hear you. You need to type. I don't know what's problem where. So I can you hear me? Am I audible?
Yes.
Okay. So what you do, you whenever you have doubt, you can just type in, because I'm not able to hear you. So I hope it's not a problem with my device.
Yeah. Hello, sir.
Okay. So yeah, so this differentiation of f at x makes sense because both of the functions product differentiation is thing. So let us discuss the differentiation of product. Differentiation of product of two differentiable function. So again, I'm not going to prove this part. Um, so let's say f of x times g of x. It is given to be two product of two differentiable functions. Now you find out. Now you want to find out the differentiation of this composition, this product. So it is nothing but this is called the product rule. First you differentiate the first part, and let's say you want to differentiate it at x equal to x naught. So first you differentiate the first part, keeping the second as it is. Evaluating it x naught, and then differentiating the second part, keeping the first as it is. Okay, that's what we are going to use here. So because both of the functions are differentiable at x not equal to 0, this differentiation makes sense. So I can differentiate, then differentiation of sine, sorry, x square times sine 1 over x can be calculated. Okay, so if I differentiate the first function, it is going to be 2x times sine 1 over x, plus differentiating the second function, I already know that it is cos 1 over x times minus 1 over x square times x square. X square get cancels out by this. So as a result, you get this thing. Okay. Now what happens when x is equal to 0. So this is when x is non-zero. Now let's see what happens when x equal to 0. Okay, so again, the idea is to we go back to the definition of differentiation. Okay, so we want to find out the differentiation of f at 0, which is nothing but the limit of this function 0 plus h minus f of 0 divided by h. Now we already know f of 0, as it is given in the definition, is equal to 0 at 0. So we substitute all these values and we try to calculate the limit of this function. So it is h square times sine 1 over h minus uh, 0 divided by h. Okay, so now you can cancel out h square by h. So you are going to, what you are remaining with is this part, sine 1 over h divided by sine 1 over h. Now how do we find out this limit? So this limit, we again use the bound on sine h, which is bounded by minus 1 plus 1, bounded above by plus 1 and bounded below by minus 1, and we divided by and multiplied with h. Okay, so that's what you are having at this moment, multiplied by h. Now you use the sandwich theorem. So because you have a function bounding your ordinal function, okay, and you have a upper bound function also. In this case, the upper bound function is h, lower bound function is minus h. So as h tends towards 0, the lower bound function goes to 0 as well. This function also goes to 0. The upper bound function also goes to 0. So it forces us, the middle function, also to go to 0. Okay, this is what the sandwich theorem is. This is what the sandwich theorem is. So I've discussed this theorem uh, before as well. Okay, so this implies that this limit of this function is going to be 0. Okay, so this function is differentiable at 0 also. So this function is differentiable at x not equal to 0, and it is also differentiable at x equal to 0. We need sandwich theorem in order to calculate this limit. Okay, so I calculated this limit by using the bound on sign, and then I multiply it by h, so that I get upper bound function and lower bound function. No, but that in that case, limit of x is tending to 0. Okay, so what you are referring to is this, when limit of x tends to 0. This is one, but we have something. We have a different situation with us, so that's why we need to go to sandwich theorem to make sense things, make sense this limit. Okay, any other question? So non-zero part, I haven't done anything much. I have just calculated the differentiation at any point which is non-zero. Okay, for that I have used this product rule which I mentioned over here. So I've used this product rule to find out the differentiation of this product of two functions. So you can see this. This is a product of two functions. Okay, the first function is x square. The second function is sine 1 over x. So you can so first you can find out the, so you need to use the product rule in order to calculate the differentiation. So now the second function is sine 1 over x. Now what is sine 1 over x? Sine 1 over x can be think of as a composition, as a composite function, which means it is a composition of two functions. What are the two functions? So first function is sine, the second function is g. What is g? G is a function, is an inverse function. You take x, so this inverse function is defined on r to non-zero. Okay, so you take a function 0 and you just consider this image with this multiplicative inverse. So this sine 1 over x can be think of as a composition of two functions. Now we apply the rule of composite. Now we apply the chain rule. So we apply the chain rule. So we get this as the derivative. So this is the derivative of x. Okay. So this is the derivative of this function. So you get this as the result. No, x naught is it. It's I'm fixing a point x naught. So I'm calculating a derivative at x naught. It doesn't matter. You can just take x naught also, but just you can take x also. Just keep in mind that it is non-zero. Okay, that's all important. So you get this derivative. Now I apply this product rule in order to get the full derivative of this function. Okay, so that's how I get the complete derivative of this function. No, this inverse function is already in the question. No? Sine 1 over x, it is already in the question. It is already in the function's definition. So what I'm doing, okay, just don't think of this gx if it's better. So just remove this whole part. What I'm doing is first differentiation of sine with respect to x, and then differentiation of, so let me rewrite it, differentiation of x of sine at this, at some point x naught, uh, and then differentiation of 1 over x. Okay, this is the chain rule. That's what I'm applying over here. So I will get cos 1 over x times 1 over x square minus of 1 over x. Okay, this is what I'm doing. Nothing else. This must be clear. Okay, so before now let us discuss some exercises, some more exercises. Okay, on the directional derivatives. Okay, so first question is that state whether it is true or false. You have a function from R2 to R, and it is a function such that the directional derivative of f along u at origin exists for all unit vectors u in R2, then f is a continuous function at 0, 0. So you have a function uh, f from R2 to R2, R2 to R, okay, uh, and the directional derivative du of f at 0, 0 of f along u at 0, 0 exist for all unit vectors u in R2. Okay, so now if this happens, then you need to prove that f is continuous. So first of all, is f is going to be continuous? Okay. So before going to solve this question, let us first recall what is a directional derivative. Okay. Let us first recall what is a directional derivative. So we define directional derivative of f in this direction u at this point 0 comma 0 to be the limit of the function, okay, f x plus y, x comma y, okay, it's a two variable function, x comma y plus u plus h times u. Note that u is a vector, okay, u is a vector in this case, it's a vector in R2, okay, minus f of x comma y divided by h. So everything is same, just you are adding your xy some uh, change in the direction of u, okay, some small change in the direction of u, you are adding that value in your xy and you are calculating the differentiation in that direction. Okay, now if this limit exists, okay, sorry, I made a mistake, this I am defining at any arbitrary point x comma y, okay, and if this limit exists, okay, if this limit exists, we define it to be the directional derivative of f along u at x comma y. Okay, so this will be the directional derivative of f along u at x comma y. Now, how do we see it geometrically? How do we see it in picture? So in picture, it has very good uh, description. Let me explain that to you also, so that it will be uh, clear in your head what do we mean by directional derivative. So I assume that you are familiar with the one variable differentiation. In particular, you are familiar with the differentiation in along the real line. Okay, with respect to the real line, assume that you are familiar with this. So, uh, when we perform a differentiation in the real line, what do we do? So we have a real axis, calling this to be x-axis, and we only have a one variable function. Okay, and our function depends on the variable x. Okay, so we have seen differentiation on one variable function. Okay, so this differentiation is along this particular line. Now this line, if I'm finding out the differentiation at x naught, you can think of you are performing a differentiation along this vector. Okay, so this is your vector, you are performing a differentiation along this vector. And how do you define this differentiation? You define this differentiation in one variable I'm talking about. So define differentiation at x naught, you are defining the differentiation to be the limit of this function. Okay, now if I make this function a two variable function, okay, let's say I add another dimension, I make a two-dimensional function. Okay, so what happens, that means I'm adding another axis to it, which is this axis. Okay, another axis being added, calling this to be the y-axis. Okay, now with respect to this axis, and your function now is two variable function. Now this point x naught will be x naught comma 0. Okay, and this direction, sorry, this point will be x naught comma 0. Okay, because it doesn't have any y direction, it doesn't have any vertical direction, so it is x naught comma 0. And uh, further, your direction in which you were differentiating earlier in the one variable case will be a vector of type 1 comma 0. Okay, okay, so it is a vector of type 1 comma 0 because you are going in the direction, uh, in the x direction. Okay, in x direction, what are the two vectors? Either 1 comma 0 or minus 1 comma 0. Okay, these are the two unit vectors in the x axis. Okay, unit vectors lying on the x axis. So if you try to write this definition, whatever definition you have earlier, if you try to write down this definition using these in this form, so how do you do that? You can just write it like this: f of x naught comma 0 plus h times 1 comma 0, okay, minus f of x naught comma 0 divided by h. Okay, so these two definitions are same. So in other words, you can think of your differentiation with respect to one variable as a directional derivative in R2. Okay, and that variable, from where that variable comes in, that variables comes from the vector, unit vector that you are choosing to differentiate along. So in this case, if I choose my differential directional derivative, if I choose my uh, vector to be 1 comma 0, the differentiation, this turns out to be similar to the one variable differentiation. Okay, if I choose any other unit vector, which is, let's say this is my unit vector u, so I replace this 1 comma 0 with u vector. Okay, and this point will again, let's say I'm still at x naught comma 0, so this will be changed. Now if I move this point also, instead of x naught comma 0, instead of the point lying on the x-axis, I choose a different point which is lying in the xy plane, neither of the x's, in some xy plane. Okay, and I choose a vector u in that, and this point is x comma y. So what will be the substitution? Substitution will be this x comma y, so x comma y and vector u. So in other words, what I will be doing, I will be calculating I will be calculating the directional derivative of f along u at this point. Okay, I hope this makes sense to you. If you have any doubt, you can ask me. Okay, so this is the theoretical part. How do we define? So directional derivative is nothing but differentiation along a vector. Yes, this is a directional derivative. So directional derivative is nothing but differentiation with respect to one variable only. And what is that one variable? What is that variable? That variable determined by the direction that you are taking. Okay. Okay. So with this definition in mind, now let's move on to discuss this question. So in this question, you have given a function, a real valued function on two real value variables, such that the directional derivative of f along u at 0 0 exist for all unit vectors in R. So let me draw the axis first and the point 0 comma 0. Sorry for that. 0 comma, so this is my point 0 comma 0. These are the axis, y axis and x axis. Okay, now it is given that if you take any unit vector, the directional derivative exists in that direction. Okay, so if you take any unit vector, let's say if you take this unit vector, if you take this unit vector, if you take this unit vector, this unit vector, this this there will be infinitely many unit vectors. Okay, infinitely many unit vectors will be possible centered at origin. Okay, so the in the question it is given that if you take any of the unit vector, the directional derivative exists. Okay, now uh, so what we have for any unit vector u in R2 at 0 0, the directional derivative of f in the direction of u at 0 0 exists. Now, what do we need to what do we need to prove? We need to prove that f is continuous. Okay, is f continuous? So, what I want to I will show that you can always construct a function whose directional derivative, okay, exists, but they are not continuous. Okay, so how do we construct such a function? So when I say a directional derivative exists, that means the derivative makes sense in this direction. If you take that back, if you take u, so the derivative makes sense in that direction. So in other words, direction in if you consider a particular direction, the derivative makes sense. Okay, if you consider a particular dimension, the derivative makes sense. But the derivative of the function may not make sense. Okay, there's a difference. If you pick a direction, the derivative of that function will make sense, but the derivative of the function, okay, may not make sense. Okay, so I will give you an example first, and then we will see how that thing is happening, and we will use this fact that the directional that in each direction the derivative will exist, but function will not be continuous. So let us consider this function fxy defined to be fxy defined to be 1 when when y is equal to 0, and else where it is defined to be x square. Okay, so first of all, let us check for the continuity. Is it continuous at 0 0? So limit of h tending to 0, fxy, sorry, so h comma k tending to 0 comma 0, f h x k, will it be equal to the 1? Okay, so if you see, it is nothing but a one variable function. Okay, so this is nothing but h square. So this limit is same as this thing, and now we know the limit of h square is equal to 0. Fine, but is it equal? Is it equal to f of 0 0? No, f of 0 0 is actually 1 because of this first condition. Okay, so this is not equal, so it implies that f is not continuous at 0 0. Okay, so f is not continuous at 0 0, that is clear. So I am starting with an example which is not continuous at origin. Now now the next claim is my next claim is that for every yeah, because what is f of hk? So f of hk is defined to be f of xy. Okay, so let me use this notation only. So this will be Now it is clear, I think so. Okay, does it now it is fine? Is it fine now? So limit of f of xy as xy tending to 0 comma 0 is equal to limit of x square as x tending to 0. And now this limit of x square is equal to 0. We know that part very well. Now, in order to say that it is continuous at origin, it needs to be equal to f of 0 0, which is not, because f of 0 0 is equal to 1. Okay, so that means f is not continuous at 0 0. Now, y is not 0 everywhere. Do you understand this definition? What does this definition is? This definition of function says that f of xy is equal to 1 when y is equal to 0. Okay, when y is equal to 0, and x square when y is not equal to 0. Okay, so what does it mean? It means that if you are on the x-axis, so on x-axis y is equal to 0, so on x-axis function takes value equal to 1. But when you are not on x-axis, okay, when you are not on the x-axis, when you are away from the x-axis, function is equal to x square. That's what this means. Okay, so so limit of f of xy, in order to say that f is continuous at 0 comma 0, you need to say that limit of f of xy as xy tending to 0 comma 0 must be equal to the f of 0 comma 0. Okay, but f of 0 comma 0 is 1, and limit of fxy as xy tending to 0 comma 0 is turns out to be 0. So these two things are not equal, so f is not continuous at 0 comma 0. Okay, now next I claim that for every unit vector u in R2, so my claim is that, no, we have used this now. We have used here that x square limit of x tending to 0 of x square. Okay, what will be this limit? This limit will be equal to 0. Here I've used that fact that here I use the definition of x fxy, which is equal to x square. Yeah, thank you. So now for every u in R2, uh, yeah, now my claim is that for every u in R2, for every unit vector in R2, du of f at 0 comma 0 does not exist. Okay, so you can see, so if I take my unit vector to be the one which is not lying in the x-axis, okay, so I break it into two cases. Now case one, when u is not equal to plus minus 1 comma 0. Okay, so let's take when u is equal to plus minus 1 comma 0. My second case will be when u is not equal to plus minus 1 comma 0. Okay, okay, so this means that when u is in x-axis, and this means that when u is not in x-axis. Okay, in the first case, if I in the first case, if I calculate this, limit, um, yeah. So what will be the limit? It will be f of 0. Okay, so it will be uh, 0 comma 0 plus h 1 comma 0 minus f of 0 comma 0 divided by h, which will be limit. First part will be f of uh, h comma 0 minus f of 0 comma 0 equal to 0. Now what is h comma 0? H comma 0 is 1. F of f 0 comma 0 is also 1. So it will be 1 minus 1 divided by h, which will be 0. Okay. So this limit is this this yeah. So this exists. Okay. So exist. Now in the second case, du of f at 0 comma 0 is again equal to limit of 0 comma 0 plus h times some x naught y naught minus f of 0 comma 0, okay, divided by h. So this condition implies that u has to be of some kind of this form where y naught is not equal to 0. Okay, so this is equivalent. This is equivalent. All these conditions are equivalent. So now you will get h of x naught, h of y naught. Okay, this is 1, correct? Okay, so it is turns out to be x naught square minus 1 by h. Okay, so there is a problem with this example. Um, yes, so um, yeah, so it will be equal to x naught square h square, x naught square. So it will be h minus 1 over h. First part will be equal to 0, but the second part, limit of the second part doesn't exist, because it's 1 over h. So this example turns out to doesn't seems to work. So we need to modify this example a bit. Hmm. But this example works for the case if I take any other point than 0. Okay, so at 0, this example is problematic. So how do we resolve that problem? So we try to shift the center of this x. So if I do that, mhm, okay, okay. So at this moment, I'm not able to make a better example out of it. So let's stop at this point. I will give you a good example next time, the next session. Okay. So let me discuss this last question, uh, today's session. So in this question number 5, uh, we have two partial derivative. We have a function from R2 to R. Okay, again a two variable function, two real variable function, real valued, taking real values. okay, such that their partial derivative exists on R2. Okay, and further the second order partial derivative also exists on R2. So then fx uh, fx by at AB, uh, then you need to prove that fx, the partial derivative of, sorry, yeah, partial derivative of x with respect to y is equal to partial derivative of fy with respect to x. Okay, so first let us recall what is a partial derivative. Okay, if you have any question, you can just ask. It is true. You are saying it is true. No, it is not true. It is false. I will give you an example where it is turns out to be false. So let us consider this example. So first, let us say what is partial derivative of fx. So partial derivative of fx is defined to be a partial derivative of fx at point x naught comma y naught is defined to be this. Okay, so basically you only change in the first variable and the second variable remain fixed. So if you only change in the first x variable, so it is called partial derivative with respect to x. If you change in the second variable with respect to y, then it is called partial derivative with respect to y. Similarly, you define f of y at x naught comma y naught to be the limit of this. Okay, now let me give you an example which will make this. So if you start with f of xy, okay, so if you start with f of xy is defined to be, uh, let's say y square, okay, for all x y in R2. So then if you first differentiate this with respect to x, what will you get? Because this is a function of a y variable, this is nothing but going to be 0, correct? And now if you further differentiate this with respect to y, you will get 0. But if you differentiate, no, this is also not a good example. I'm sorry. uh, why it is not a good example? Because if you again differentiate it with respect to x, you will differentiate it with respect to y, you will get this 2y, but once you differentiate with respect to x, you will get 0 out of it. So it is not a good example because it is turns out to be same. I want to give you an counter example to this. So yeah, so we add some, let's say x cube. If I add into this, so what will I get? If I differentiate, it will be 3x square. Okay, let's consider this mixed derivative. So if I differentiate this, I will get y square, and if I differentiate with respect to y, I get 2y as a result. Now if I differentiate with respect to y, I get, oh, I'm doing something horribly wrong. So I'm basically taking functions which are whose partial derivatives are continuous. So the trick is to take functions whose partial derivatives are not continuous. Okay, so let us take, So in this question, the partial derivative exists on R2. Similarly, the second order partial derivative also exists on R2. Okay, so let's uh, go a bit backward. So if I say that this is something like 2, this is something like 0, and differentiating with respect to y gives with respect to x gives me this, differentiating with respect to this gives me what, let's say this is same to y. So but then this implies that function has to be some 2y, some y square, correct? And this implies the function has to be some 2yx, so that its differentiation is like this. So if I take this summation, if I differentiate this thing, so I will get 2y, and if I differentiate this, I will get 2x, correct? Factorial 2 will appear, correct? This again, the continuous is differential, partial differentials are also continuous, so it won't give you, won't gonna give us the thing. So the trick is to get the partial differentials not continuous. So something like, okay,